Start the recording and pull up GNU plot. All right, so this here, all right, we have so the first things that we are most interested in, we have Kirchoff's laws, right? If we can spell his name right, Kirchoff's laws. Make sure that it's recording. The recording. We are recording it. Good. And is it on screen? All right, it is indeed on the screen. Okay. So Kirchoff's laws. There are two of them. We have usually sometimes these guys shorthand to KLL and KLJ. That is Kirchoff's laws loop and Kirchoff's law junction. Get down here, right? So we have the loop law says that if we have a battery, if we have a loop, if we have a circuit with its components in it, such as a battery, a resistor, come here, a resistor, wire over, wire down, resistor, there's a resistor, over and back. So we go around this loop here. The sum of voltages across all of our components here is equal to 0 volts. This is equivalent to, this is a consequence of energy conservation. Energy conservation. So the battery, let me put down battery properly here. We have a battery here. This is positive V volts here. And the resistor, like so, is equal to the, let's see here, current times resistance, IR. This is the voltage of the, across that resistor, and it is negative. So as you go around the loop, if you sum up all the parts around here, we have a pump up of an energy and then a draw down of energy as we go around. And so this is a energy conservation, a consequence of energy conservation. The other law is a junction law. It says that current coming in, going here, it says current comes in this way, and then must leave out these guys here. So this is an I1 here, and an I2 here, and an I3 here. So the junction rule says that if you sum up all the currents coming into a junction, the sum must be equal to 0 amps. This is a consequence of, there's a variety of way to put, there's a few ways to do it. You can do this as mass conservation, and of course I grabbed the whole thing there, didn't I? Yep, I did. There we go. Mass conservation. It's not electron conservation because we can violate that, but we can't violate lepton conservation. Under certain conditions, this would also be a particle conservation. There's a few ways to write this one down, but the basic idea is that if we have electrons coming into the junction, they must leave the junction, and so all the current, so this the sum of i's coming in, and the sum is equal to the sum of the i's leaving. And so that's the idea of the Kirchoff laws. So, all right. Well, it turns out we can then use Kirchoff's laws to prove a certain idea about say resistors. So if I have a potential here, it goes up, and then say we have some parallel resistors like we had. So for a parallel circuit, R1 and R2. And we have a voltage here. All right, well, in this case, that means that we have the voltage. Come here. There we go. So the voltage drop for both of these resistors here has to be equal to the voltage increase from the battery, because we have to go around this way. There we go. There's our current going, our loop this on for R1, and then we go around the outside, and we also have this loop here for R2. So that means that we have V is plus V, yeah, so V battery is equal to VR1 is equal to VB plus VR2, and this is equal to 0 volts. Well, so if you rearrange these, that means that the voltage on the battery is equal to the resistor, voltage on resistor 1 and the voltage on resistor 2. So that means that we have R, so yeah, so VB equal plus VR1, move that to the other side over here, and VB plus VR2, move that to the other side there. That means that VB is equal to negative VR1, and that is equal to negative VR2. Well, if we impose Ohm's law on this, that means these are equal to I1 R1, and that is equal to I2 R2. Well, these guys are equal to each other, but there's a way to think about these guys as a whole here. So if you look to the junction rule, going here, we have I1 plus I2, so that we can have an I1 go this way and an I2, try that again, write that down a little different, and an I2 over here, like so. Oh, so that means that, so this is an I total here that's going in here. So this is an I total now. I total, so, well, we can combine these together into one resistor, so that means that we have V is equal to I total R total, and that and this one here is a there should be, yeah, so and then so that I total is equal to I1 plus I2 RT. All right. Well, I1 is equal to the V divided by the R1 there. So that becomes V over R1 plus V over R2. And this is equal to RT. And that's equal to V. Yeah, we got exactly where I want to go. Very good. Divide the RT to the other side, and then cancel out all the V's. So we have that V over RT is equal to V over R1. Uh-oh. Something happened. Oh, look at that. We got people coming in here. Admit. Who am I admitting? Pierce is here. Very good. Alright. Where was I? I was tapping on. Right. V over RT is equal to V over R1 plus V over R2. Oh, well, those V's can all cancel out. They don't mean anything anymore. Don't gone and gone. So we end up with that 1 over R total is equal to 1 over R1 plus 1 over R2. So that's what it is for two parallel resistors. So in general, when we have parallel resistance, the total resistance is equal to the sum. So 1 over the total resistance is equal to the sum of 1 over all the resistors, all the parallel resistances. Pierce, how you doing there?
I'm good. I just saw your email.
I sent
And
that one.
I was like, oh shoot. I just saw it and
Well,
I was like, better log on.
yeah. Well, Akila got here about 16 minutes ago, and I was ready to go 30 minutes before that. So,
Yeah.
anyhow,
Sorry about that.
you don't have to have your mic on for this if you don't want, but you'll need to turn it on because I'm not looking at the chats and whatnot. Because I'm drawing on a separate screen on a separate application. I can't see anybody asking questions. Akila went away. That's no good. Oh well. So if you got a question about what's going on here, I'm trying to be simple but short and sweet about what we got going on here, so that it's not a lot of stuff for people to watch tomorrow. We have Kirchoff's laws. Kirchoff's laws. We have there's two of them. One is the loop. One is a loop rule. Come here, grab there we are. One is loop rule. So as you have battery and you go around the loop of a circuit through a resistor, it comes back around the other side. The sum of voltages on everything in your loop there is equal to 0 volts. This is a consequence of energy conservation. So your battery is increasing the potential on electrons, and then it goes around and it comes out the other side as current flows, and then they drop their potential going through the resistor, and then they have to go back around again. And then there's Kirchhoff's law junction, where current coming into the junction has to leave the junction, so that the sums of currents going through your junction here is equal to 0 amps. This is a conservation. The one that's important to you guys is this is conservation of mass, but there's a few other underlying quantum mechanical rules for that. And so I have just now finished proving the the resistance of parallel resistors. And so, having done that, I'm going to do it again for a series. Come on, where you have it? Alright, there we go. So, over here just a little bit. Alright. So, drop that. Very good. Pencil back. So now, on to the alternative case where we have resistors in series. So we got our battery, got resistor 1, goes around this way, goes over here. Resistor 2 goes around this way, over here. So we have a VB here, resistor 1 here, resistor 2 here, and current goes around the outside like so. Alright, so we got some current. Well, okay. So we have the VB plus, let's go minus. Minus VR1 minus VR2 is equal to 0 volts as we go around the loop. Well, I suppose at each point along this wire here and through the resistor, that is a two-way junction. So, this little bit of wire here, current comes in, and the current has to go leave out the same way, right? So that means that the current going through R1 has to be the same for R2. V is equal to I on R. Yeah. So now we have that VB I should go ahead and set that equal, move those to the other side. So the VB is equal to I divided by R1 minus plus I divided by R2. Well, VB is equal to, well, it's looking at the resistance of the whole circuit, and it's got some current flowing through there. So that's going to be I is over RT. Something funny to me. Resistance parallel. VB This should not have ended up here. V equal IR. Oh, right, because that's not Ohm's law. Try that again. V equal IR. That'll get me 114 I times R1 plus I times R2. And this this is going to get some current through here, and it's going to get it with a total resistance, where that might be. Well, that I is the same for the whole circuit. So that means I can factor out the I on both sides, or divide out the I's as necessary. And so it turns out that R1 is equal to R1 plus R2 is equal to my total resistance. Okay, so now if we have resistors in series resistance, the total RT must be equal to the sum of all the resistances in that bit. Okay, well, turns out there's another way to look at this. The total resistance for any resistor is equal to the resistivity times the length divided by the area. Oh, well, the length is here on top. So basically what I'm doing here in a parallel case, in the series case, is I basically took one resistor and I made it longer by adding a second resistor in that way. Alternatively, with the area, if I have my battery and it goes through a little bit more. Battery goes there, and then current goes through one resistor, and then it goes through another resistor. Oh, basically what I've done here is if I've added the area of these two resistors together, and I've got a bigger area for this one resistor rather than a smaller area. And so we basically come up back over here to a parallel resistance because of how the resistance is constructed. Make sense there? Any questions on that? Oh, good. Clee's back. Questions? Make sense? Hearing none. So we got the resistors, we got the Kirchoff's laws, loop junction, energy conservation. Okay. Well, I suppose a good idea at this point would be to try it out. Do you want to try it out? Yeah, let's try it out. Okay. Let's see here. I would like to do example 12. Example 12 is an excellent choice in this case. Okay. Delete that out. Alright, give me back my pencil. Example 12. Okay. So I have a battery. It goes into a resistor. And then it comes down through another resistor, and that joins back to the battery. And then we go over here, we got that bit there, and then we go through one resistor and another resistor. And so this is here. This is 110 ohms. This one is 220 ohms. This is 250 ohms. And this is 180 ohms. Okay. What's up? Alright. So, well, the first thing we need to do is we need to take care of these guys. These guys are in series. Okay. Well, the series rule says that we add them together and get our total. So that means that we now have a battery. That's a capacitor. Let's try making a battery. There we go. Resistor. down, resistor, down, over, back, and over and down, resistor. Okay, so now this is 180 ohms. This is 110 ohms. And this is the sum of those two. So 220 plus 250 is 470? It is. So now I have this to be 470 ohms. Now I grab these two. They're in parallel. There's probably more than one way to do this. But I'm not feeling like doing topology today. So these guys are in parallel. Goes over, resistor, goes down, resistor, goes over, and back up here. Okay, these guys are in parallel. So now, I have 1 over. So I have this guy over here, way over here. So I'm just going to go ahead and do the inverse on that. So now we have that RT is equal to the inverse of 1 over 470 ohms plus 180 ohms to the inverse, like so. And the answer is, I don't know. Book does, but I'm not going to ask the book. 1 over 470 plus 1 over 180 in an inverse. That's 130 ohms. 130 ohms. So this guy here is 130 ohms, and this guy here is 110 ohms. All right. Now we're back to our guys in series. I heard something. What was that?
How come we're doing the inverse?
This inverse right here?
Yes, the RT.
Right.
The 1 over 470.
Yeah, so this goes back to our parallel resistance right over here. This guy right here. And so we want this RT guy right here. So it was 1 over RT is equal to 1 over 470 ohms plus 1 over 180 ohms, like so. Well, to inverse this guy, we can just do that, which means we have to also do this. Do I need to go over the math of the power rules here? Because that's math 118, and I'm teaching that.
Yeah, I know how to do that.
All right, and so that means we're back up to here. Anyways, so that's 130. So now we have these guys in series, and so now we have to apply the series rule. 130 plus 110, that is 240. 240 ohms, like so. And in principle, I could actually build that because I believe those resistors are in front of me. And so we check that. Flip. I'll leave it there. What do we need? I need a 110. 110 does not exist. Never mind. I can't build that. That's not a thing that. Yeah, there are no 110 ohms out there. Never mind. There are 220s, right? Yeah, there's 220. There's 250. Nope, no 250s either. But there's a 180. So 2 of those resistors are common and 2 of them are not. Anyhow. So I guess I won't build that. Anyhow. So that's example 12 and how we apply the parallel and series resistances to that stuff. So there is time is presently Tuesday. Been at this half an hour. Good. Well, if we can build circuits with resistors, we can also build them with capacitors, right? So let's get rid of the example. Okay. So, how am I doing on battery here? I did not bring a charger for my laptop. We're doing good. We're doing all right. Okay. So, going back to Kirchhoff's laws, we can have, say, a battery. Goes up, over, down. We have a parallel plate capacitor, or just any capacitor there. Go over, and we make another capacitor, like so. Okay. So, these guys, they're going to charge up, and they're going to have the same potential as the battery. So, okay, well, that means we have that VB is equal to VC1. C1 on that one, and C2 on that one. And that is equal to VC2. Well, I'll try again. C2. C2. Okay, well, so it turns out that these guys, potential is equal to, what is it equal to? Let's see here. The charge itself is equal to CV. So that means that V is equal to C on Q. Oh, okay. So then this is equal to C on Q, and that is equal to C on Q, right? All right. Did I do it right? No, I didn't. Q on C. No, I did wrong. Q on C. There we are. Q on C. There we go. So this is equal to Q on C is equal to C1, and that is Q on C2. Okay, these guys are equal to each other, but I want the total capacitance for these guys. Okay. So let's see here. I believe these guys are not the same. Yeah, these guys are not the same. Q's are not the same. These are, but they are equal to each other. Q2, and so that has to be equal to VB, and so this will be equal to Q3. Current goes where it needs to. Q's are doing what they need to. It's actually the same. Hold on. These guys are in parallel. I should not end up there. These should end up with this looking like a series. What am I missing here? These V's are correct. Why am I having problems thinking through this? I'll bet it has something to do with the current here. QT on CT, and so we end up with that I1 plus I. Try again. I1 plus I2 is equal to I total, but it turns out that so there's some calculus involved with these guys here, and so it should be possible to basically say that so if we sorry for the calculus I'm about ready to impose on you, but we're just going to write it down and to slightly ignore it. We're basically adding up all the current that flowed over a certain amount of time. Basically what we're doing here. So how much current has actually, adding up the current that flowed, we end up with that Q1 plus Q2 is equal to Q total, and then I can make use of this guy, here, and we find that these guys are equal to C1V plus C2V, and that is equal to our C total V. There we go. That works. So we're going to add up all the current that flowed over a certain amount of time, through both these guys here, and we're going to add all up. And so we end up with a Q1 plus Q2 is equal to our Q total. Oh, well, I suppose that makes sense. The Q that ended up on an equivalent capacitor has been distributed to these two capacitors here. Oh, look at that. They have the same voltage on all of them. Well, I guess that means we can cancel out that voltage there. And we get that CT is equal to C1 plus C2. Well, we can keep going on that if we want to. So that means that if we have... usually get a little more space. If I have try again. Parallel capacitors. Well, the capacitor total is equal to the sum of all the capacitors. And if we do this number for our do this in series, grab this, delete that, grab that, and so now if we do one battery, a battery I say, and run that into a capacitor, like so. Well, now as I go around, my VB is equal to, hopefully I don't do the calculus thing again, VB is equal to V1 plus V2, and what was it again? That was Q is equal to CV, so that means that V is equal to Q over C. Yeah, good. So now I can impose this guy into here, and we get that Q1 over C1 plus Q2 over C2 is equal to some Q total over C total, right? Well, turns out that if you're going to push charge out this way around our around the circuit, you're going to get charges here, and they're going to push some charges off this side, and they're going to push charges over here, and they're going to induce charge over here. So that means that if we, whatever this Q is, and whatever that Q is, they have to be the same. Otherwise, this Q came from, if this Q2 is greater than Q1, that means that this Q it had to pull charge from nowhere. And that doesn't make any sense. Q2's charge came from Q1, that came from the battery. So that means that this guy, all these Q's are the same. So that's Q over C1 plus Q over C2, and that is equal to Q over C total. Now we cancel those guys out. Oh, so we can just keep going if we needed to. So it turns out that our series capacitance is that 1 over CT is equal to the sum of 1 over CI. So these guys have traded places because the voltage is equal to Q on C, but for a capacitor, but the voltage for a resistor is I times R. So the capacitance for the voltage for capacitance has this capacitance on the bottom, has this quantity on the bottom, whereas so it's dividing by the quantity. But for a resistor, we're multiplying by the resistance. So because these guys have traded positions, that means that their parallel and series have traded orders. But there's another way to look at this. Capacitance for a parallel plate capacitor is epsilon naught times the distance, times the area over the distance. And so in this case, if we have these guys, we're basically making these guys come together for our distances. But if we have I was hoping the parallel plates would have been easier to do, but no, it had to be harder. Like so. So basically, in parallel, these guys' area, they're basically adding together, like that. Anyhow, Is there anything else I want to try here that I really want to point out in particular? There are some things we're going to get to in due course. How long has my recording been going for? About half an hour. Okay. Let's do two problems that I find to be of particular interest. One is going to be a Kirchoff's law rule, which is going to be really important for us to figure out. And let's also do an example of a network of capacitors, and then I think I will call it quits there. But it's going to take us a hot minute to go through the Kirchoff's law, I can tell you that. Because I'm going to have to explain what's going on, so it's going to be take us a hot minute. Alright. Kirchoff, we're going to do capacitor network first. I didn't see an example of a good capacitor network in the book, but there is an excellent choice in one of the problems for a capacitor, and so I'm going to grab, this is 20.97. 20.97. We have plate goes here, plate goes there, around the bend, plate goes there, plate goes here. Back it up just a hot minute so I can. There we go. Plate goes there. Comes, oops, too far. Capacitor goes here. Capacitor comes here. Make that actually capacitor. Make this actually capacitor. Yeah, there we go. And there we go. There we go. So this is 5 microfarads. This is 24 microfarads. This one is 12 microfarads. This one is 8 microfarads. This one here is 4 microfarads. And this one here is 6 microfarads. Okay. So, we need to grab these guys here off these three here off the back end. These guys are in series. So that's 1 over. So we're going to have capacitor goes here, capacitor goes there, capacitor goes there, capacitor goes there, around like so, up there, up over here, da da da, like so. Doink. Oh, we don't need that. Doink, doink. This is 4, 6, and 5, and this guy is something. Well, he's going to be 1 over C total is equal to 1 over 24 microfarad plus 1 over 12 microfarad plus 1 over 8 microfarad. And well, I want the CT, so minus 1 goes there, minus 1 goes there. So I get that CT is equal to, I don't know. And the book doesn't either. That's fine. 1 over 24 plus 1 over 12 plus 1 over 8 to the inverse is equal to 4. Oh, okay. So this is 4 microfarad. Yeah, that guy goes 4. So we grab these two. They're in parallel. All right. So that makes that easy. That's 4 plus 4. 4 plus 4 is 8. So we now have a network that looks like that. And so we have 5, 8, and 6. And so now we need to do, so this CT going here to that guy is CT is equal to 4 microfarad plus 4 microfarad. All right. Now watch this, 1 capacitor. So that gives me 1 over CT, as before, just like this, but with different numbers, is equal to 1 over 5 microfarad plus 1 over 8 microfarad, there, plus 1 over 6 microfarad, all to the minus 1. CT is therefore equal to Begin 1 over 5 plus 1 over 8 plus 1 over 6 and to the inverse. 2.03. 2.03 microfarad. Questions about that? Hearing none, let's find out if you're also still there. Oh, the key is out again, or something like that. Somewhere. Google's not entirely saying if Q is still here or not. Alright. So, this one is, let's do a rather important problem. Let's make use of Kirchoff's laws, and then I think we'll call it quits there because my voice is getting a little toasty. Okay, well, alright. Kirchoff's laws. Let's grab right. I'm going to grab number 81 here. So this is 20.81. We have a resistor over here, a resistor over here. This guy up here is 1 ohm. This one is 2 ohms. And this one here is 3 ohms. I'm going to put a battery here and a battery pointing the other way there. So this is 1 volt goes here and 4 volts goes here, and then we connect it all up. Alright, so I have this lovely system here. How do we solve a Kirchoff's law problem? I would like to know I would like to know the potential across all resistors. I would like to know the current in both batteries. And I would like to know the current in the 1 ohm resistor. Did I hear a question? Nope, I hear no questions. All right. Okay, so how do we solve a Kirchoff law problem like this? All right. Step number 1. Select, if I spell right, good heavens. Select independent loops. Independent loops. What in the Sam Hill I mean by that? All right, so and their directions. Alright, so this guy here, this battery says we're going to push this way. This battery says we're going to push that way. The 1 ohm resistor is not saying much of anything, so we'll just say that the current going through here is also going that way. Okay. So now I'm going to select 2 loops that satisfy these currents here. Okay. Well, I got one that goes around the outside here, like so. I've got another one that goes around the inside of this lower one, like so. These are my 2. I'm going to recommend these 2 independent loops. There is a third that I'm not going to use. The third is this guy right here. Right? Oh, not that way. I'm going to go the other way. I'm going to assume the current would go this way. Well, that's an opposition to the current that's going through here. Well, that just means that instead of so that's going to if you were to select it, that's going to have an impact on the next step. Step 2. Is it no, not next. It's going to have an impact on a future step. First, we have to go select a. We're going to select independent junctions. This circuit has 2 junctions. We have this guy here and this guy here. For no particular reason, I'm going to select the one on the right, but they mean the same thing, right? They're doing the exact same things. That's why these junctions are not independent. But there's only 2 of them. So I'm going to grab this one here. That's the one I'm going to be most interested in, the one on the right. Step 3, write down Kirchoff's, if I spell it right, Kirchoff's laws for loops and junctions. I suppose actually that's not entirely perhaps this is not the best way to do this. Let's back up just a little bit. Step 1, select the independent loops. Scratch this guy right here. Select the independent junctions we're going to look at. So I'm going to select, for loops, I'm going to select this one and this one. And for junction, I'm going to select this one here. Number 3, we're going to assign, we're going to guess currents. We're going to guess the direction of current. I have guessed that the outside loop here is going to have current going in the counterclockwise direction, and this loop here is also going to have current going counterclockwise, and so that means that current is going to come into the junction from below here, and it's going to leave to the left and up. It is not important that you guess your current correctly. If you guess wrong, that means that you're going to get a minus sign at the end, and you just go, oh, I was wrong about this, the current's going the other direction. My bad. That's fine. There's nothing wrong with making a bad guess at that point. Then we write down our Kirchoff's laws. Kirchoff's laws. All right. You're following some rules. discharging batteries are plus V charging batteries are minus V. Three. Current in resistors agreeing with loop are minus IR, and for current in resistors disagreeing with loop R plus IR. Alright, so what we got going on here? Well, for my outside loop, what we got? We have, we're going to start with I like starting with the battery. It keeps things simple. It's easier to mark down what battery you start with, and so you know when to stop and come back. So, equation 1. 4 volts, as you go around the outside, is minus 1 ohm I1 minus, coming through this guy here, 3 ohm I3 is equal to 0 volts. Starting at, once again, the 4 volt battery and going around the lower loop, we have 4 volts minus, I believe that's going the right way. Yep, minus, not minus, plus 1 volt. Then we go through the 2 ohm resistor, minus 2 ohms I2, and we come back down through the 3 ohms again, minus 3 ohms I3 is equal to 0 volts. So in this particular case, all of our resistors, the current I'm supposing is also agreeing with the direction when we went through our loops. That's fine. And then the junction rule we have, I erred. Instead of doing this one, let's look at we'll keep this one here. So this current here has to come through this 3 ohm resistor, right? So we have that 3 ohm, that I3, and then coming out of this junction, we have the current going through 1 and also 2, minus I1 minus I2, and this is equal to 0 amps. Okay. So now I have 3 equations and 3 unknowns. The unknowns I have are all the currents here, but I also have this potential across my resistors. We'll come back to that guy there. Not particularly interested in that just right this very moment. We'll find those with the potentials with Ohm's law here in due course. Come here. There we go. Okay, well, all right. Well, now we got this monstrosity here. Right. There's a variety of way. There is no one wrong. There's no one right way to solve linear equations. There are a great many choices. However, some choices are better than others. In this case, I'm going to number these guys off. 1, come on, 1, 2. Actually, let's not do it that way. This will be I. This will be II, and this will be triple I. Okay, I'm going to take the difference here. I'm going to subtract 1 and 2. Alright, well, what's that going to get me? Well, if I take the difference of 1 and 2, it removes these 4 volts here, and it removes these guys here off the end, leaving me with these guys in the middle. Is that going to do what I want? Hold on. It's going to mean an I2 and an I... butter. I'm just trying to figure out how best to go about this, and I don't think there's a good one to do for this at all. Yeah, bugger. Is that what I want to do? No, I'm not going to do that. I'm going to solve for this I3 here. Alright, so I3, solving for I3, well, that has to be I3 is equal to I1 plus I2. Well, that makes good sense. The current going through I3 has to be the current going to I1 and 2. That's fine. And then I can take this and put it into these guys here. So now I have 4 volts minus 1 ohm I1 minus 3 ohms I1 plus I2. I'm going to go ahead and simplify this down, and we get that 4 volts is equal to not equal to anything, is minus 4 ohms I1 minus 3 ohms I2, and that's still equal to 0 volts. 0 volts is still equal to, well, 4 plus 1, that's 5, so 5 volts minus 2 ohms I2 minus 3 ohms I1 plus I2. And that has to be, well, so, expanding this out and collapsing down, we have that as 5 volts. Minus 2 minus 3 is minus 5 ohms I2 minus 3 ohms I1. Alright. So now I have these two guys here. We got so these are our I1s here, and those are I2s. Oh, well, that's not very helpful. That's not the best way. That's not friendly. 3 and 5 are prime numbers, so there's not a lot of good choices here. Primes. Not good choices. I'm going to solve for this one right here. This I1 here. Okay. So throw these guys to the, no, throw this one to the other side. And then divide by 3 ohms, so that I1 is equal to 5 over 3, that's, just 5/3. 5/3 amps minus 5/3 I2. I'm going to take this guy and I'm going to throw it in here. So now I have that 0 volts is equal to 4 volts. Oh, 20% battery. You can bugger off. 4 volts. Where was I? Minus what was it? 4 ohms times these guys here. That's 5/3 amp minus 5/3 I2. And now I need to expand that out. So that's 4 volts minus 4 times 5 is 20. 20 thirds volts. Yep, that's a volt there. Minus 20 thirds I2. Okay, add these guys together and then throw it to the right hand side. That'll be 4, come here, 4 minus 20 over 3 is that, oh, really? Oh, okay. Go ahead and multiply that by 3. We have negative 8 thirds volts. So this is equal to negative 8 third volts minus, oh, minus here, minus there. So this is not minus up here. This is a plus. Plus 20 thirds I2. Okay. Throw that to the other side and multiply by 3. We need an ohms on that, right? Yeah, ohms goes there. And so an ohms goes here. So now I have that I2 is equal to 8 thirds 8 third volts times 3 over 20, 1 over ohms, and that'll give me an amp. The 3's cancel here, and pull the 4's out. Yeah, pull the 4's out. That's a 2 there and a 5 there. So this is 2/5. 2/5 of an amp is I2. Okay. So then up here we have this is 5 thirds amp minus 5 thirds of 2/5 amp. This fifth and this 5 and this fifth go away, and so now I have this is 2. This is 5 minus 2 is 3 thirds is 1 amp. Is my I1. So now I come up here and we find that I3 is the sum of these two, so that's 1 amp plus 2/5 of an amp, and so we end up with that this that's 5 7/5 of an amp. All right. Okay. So now I got all my currents. So I have. So now I have that. Sorry, not R1. I have that I1 is, where do you go? 1 amp. So I got 1 amp going around on top. The current going through resistor 2 and a 1 volt battery is 2/5 of an amp, and the current coming back through this resistor here on the bottom and going back through the battery here is where do you go? 3 is 7/5 of an amp. So I have all the currents. Now I want all the potentials across all the resistors. Okay. Well, I guess we can get rid of all these guys right here. Delete that. Delete that one. And that one. And now we can do, now I can do all the potentials here. Okay, so on this one up here on top, we have that I1 times times R1. Well, that's just I1 is 1 amp, and its resistance is 1 ohm. So that means that it has a potential across it of 1 volt. I2 times R2. Well, that's 2/5 of an amp times resistance of 2 ohms. So that's 4/5 of an amp. That's 4/5 of a volt. And I3 R3 is equal to is 7/5 of an amp and 3 ohms. And so that'll be 21 over 5 volts. 21 over 5 is what? 21 over 5 is 4.2. 4.2 volts goes here, and this one is 0.8 volts if you were so inclined. And so that basically comes down to the basic last step. Once you've written down your Kirchoff's laws, step 5, we are looking to solve for requested values. And I think that's a good place to stop. Do we have any questions about how to solve those, guys?
No, I'm able to follow through with what you're doing.
Okay. Oh, okay, yeah, we're good. I was just wondering if I accidentally wandered off the screen there a little bit. The answer is no. All right. That sounds like a good place to stop. We will talk about this stuff some more come Friday? No, Thursday. All right. See you on Thursday. Bye.